In this video, we're going to be looking at linear programming. Linear programming is pretty similar to the linear systems of equations that we've already looked at, with the difference being that for these, there are going to be infinitely many solutions, and we want to maximize the amount of profit. So we want to find the most, in this case. For other examples, it might be the least, so we might want to minimize costs or maximize revenue or any number of things. So for this problem, we're looking at the Olympic Ski Company, which makes skis and snowboards. And so the first thing we want to do is come up with some equations here. There will be one equation. There will actually be a number of linear inequalities that we'll want to come up with as well. The first thing we always want to look at with word problems is what are the variables. Now, the variables are going to be skis and snowboards, and that's generally what most people say when you ask them what the variables are. But there's a lot of things about skis and snowboards. We want to be specific. For this problem, our variables are how many skis and snowboards. So in this case, x is going to be the number of skis, and y is going to be the number of snowboards. So we need to know that before we can start anything else. All right, so the next thing we always want to look for in word problems are the totals. So we want to look for, we're going to be combining some things that will equal something else or be less than or equal to something else or something of that sort. So we want to find our totals. So for this problem, we see that skis require some fabrication hours and some finishing hours. Snowboards also the same. It tells us the profit of these things. And then down here it tells us that we have 420 labor hours for fabrication and 36 labor hours for finishing. So those are going to be our two totals: total number of labor hours, total number of labor hours for finishing. So what we're going to start with is, we'll start with 420 on the right of the equation. Now that's 420 hours for fabrication. So, all right, that's for fabrication. So the left-hand side of my equation also is going to be numbers that deal with fabrication. So I see that skis have 12 hours of fabrication, snowboards require 10 hours. So if we use these variables here, that's 12x plus 10y less than or equal to 420. So now the next one, we have a total of 36 labor hours for finishing. So we're going to start with 36, and that's finishing. And I would recommend always writing down what the units are here, so that way you can make sure everything in the equation is the same. So this is a fabrication number, this is a fabrication number, and this is a fabrication number. And we want to do the same for finishing. So for finishing, we have 36 labor hours available. Both skis and snowboards require 1 hour. So that's going to be just x plus y, and since we have only 36 available, that's got to be less than or equal to. Now these won't always be less than or equal to. Sometimes we have minimums that we want to have at least something of something. In this case, we have 420 hours of fabrication. We can't use any more than that, but we can use less than, and the same for finishing. All right, so now that we have our two equations, or two inequalities rather, we want to come up with what we're trying to maximize. So we're trying to maximize profit in this case. So let's look at our profit numbers. Skis have a profit of $60 and snowboards have a profit of $55. Now this isn't going to equal a number. This is just going to be what we're trying to maximize. And so usually the way we write it is z equals, and then we write down our objective function is what it's called. So this one's going to be 60x plus 55y. Okay. All right. So now there is one other thing that I skipped over. So we have our inequality for fabrication. We have our inequality for finishing. We also have our non-negative constraints. And the reason we need our non-negative constraints in this case is because we can't make a negative number of skis or a negative number of snowboards. So we're constrained that both x and y have to be greater than or equal to 0. So once we get to this point, what we want to do is take these two inequalities, the top two, and we want to solve them for y. So we will take the top one, we'll subtract 12x from both sides and then divide by 10. And so what we'll end up with is y is less than or equal to 42 minus 1.2x. And then for this equation, we're going to subtract x from both sides, and we'll get y is less than or equal to 36 minus x. And so let's go ahead and number those and color code them. We'll make that one y1 and this one y2. So we'll have the blue and green lines when we graph them. All right. So let's draw a graph, and we can graph this in our calculator. So let's go ahead and go over here and do that. So we'll put these in under y equals. So we got 42 minus 1.2x, and then 36 minus x. And I'm also going to put the x-axis in here as well. That'll help us. So y3 is going to equal 0. That's our x-axis. So we'll hit graph, and we're not going to see anything because it's not zoomed out enough. So I would always start with zoom standard. So if you've got any other zoom other than this, I would go to zoom standard first. Then we'll zoom out. And now we can see. All right, so basically what our graph looks like is we've got a line here, and then another similar line that comes over and crosses it right there. Now, both of our lines are less than or equal to, so we know they're going to be shaded both in the down direction. So first thing we want to figure out is which equation is which. Now this is pretty easy because the y-intercepts are already here since we had this solved for y. So y1 is 42, that's a higher number, so I know that y1 is going to be this top equation right here. And then for the bottom equation, that one's going to be y2. Now again, we have both of them are less than or equal to, so we're going to shade below y1. And then y2 is less than or equal to, so we'll shade below it as well. Now again, we're not looking below the x-axis or to the left of the y-axis because that is outside of our feasible region because of our non-negative constraints. So our feasible region is going to be this area in here, the blue and green area. So I'll highlight it in red. So this is kind of going to be our feasible region. With corner points where those two lines meet, corner point down here, the x-intercept of y1, corner point over here, the y-intercept of y2, and then 0, 0, which is not likely to maximize our profit, but is technically one of the corner points of our feasible region. All right, so now what we want to do is find the intersections here. So we'll go over to our calculator, and we'll hit second and then trace down to intersect. And we want to select, let's first find the intersection of y1 and y2. So we've got y1 up here, we'll hit enter, and then y2, we'll hit enter again, and enter one more time, and it shows the intersection is 30 and 6. So this point right here is 30, 6. So that's our first point. This point up here, the y-intercept of y2, we already know that one, because this is in y equals mx plus b form. So that one is 0, 36. Of course, we know 0, 0. And then our last one, we can find that one by using the fact that we put in the x-axis as one of our equations. We can find the intersection of, so that is line y1. So that's the x-intercept of y1. So we will select y1, and then select y3 and hit enter, and what we get is at that point is 35, 0. So that's our last corner point. All right, so here are our 4 corner points, and so again we're going to be using our objective equation, our in this case profit, z equals 60x plus 55y. And so what we're going to do is we're going to plug in each of these numbers into this equation to see what we get. So we'll plug in 0, 36. So we do 60 times 0 plus 55 times 36. So again, that's this point over here, 0, 36. So we plug that in, and what we get there is 19 80, so that's a profit of $1,980, and that is if we make 0 skis and 36 snowboards. So then we'll do this point here, 36, so we'll do 60, plug in 30 for X, and 6 for Y. And what we get there is a profit of $2,130. We'll then plug in 35, 0. So that's going to be 35 skis and 0 snowboards. And we get a profit of $2,100. And then we can plug in 0, 0, but we're obviously going to get a profit of 0, so that is definitely not going to be our maximum. So in this case, our maximum profit is going to be right here. Our maximum profit is $2,130 at the point 36. So for Olympic Ski Company, if they want to maximize their profits with the labor hours available, they should make 30 pairs of skis and 6 snowboards, and that would give them a profit of $2,130. Now for this problem, we had a bounded feasible region, meaning there were lines on every side. When this is the case, we will always have a maximum and we will always have a minimum. So in this case, the minimum is 0 by producing 0 skis and 0 snowboards. If we have an unbounded region, so for example, if both of these were greater than or equal to signs and our shading was in the up direction, we would have a minimum but not a maximum. So if our feasible region is unbounded, we will have either a minimum or a maximum, depending on what the graph looks like and what the objective equation is. But if we do have a bounded feasible region, there will always be a maximum and always be a minimum. In this problem, all we care about is the maximum, and that's the maximum profit that we could get.